Okay, good morning, everybody. So this is the second day of the second week. Okay, so today we have very good speakers, and I hope that you people are enjoying and getting something, learning. Say yes or no something. Okay, fine. So we have the first speaker today, Dr. Rajib Chattopadhyay. He is currently senior scientist at IITM Pune, and he did a master's from BHU, and then he did PhD from IITM itself. He spends a few years in US as a postdoc, and then he became a scientist in IITM. And he also spent 4 years in the IMD as a head of one of the department and as a deputation. And his research area has, I mean, long list. I have to read it. So
No need.
He's working, I mean, the core research area is the prediction and the diagnostic of the monsoon subseasonal to seasonal variability, and working on the climate data application, climate models, and the machine learning models, and the large scale telecollections, land atmosphere modeling, tropical and extratropical interaction, and the role of mid latitude waves on the heat waves. So he has done a lot of work when he was in IMD. He has developed many models and the product for the heat wave and I think heat stress. Also, he's working with the Professor Ravi Nanjandoya. Yesterday he was talking. So he has a lot of knowledge. So you can, I mean, have the opportunity to discuss with him and to learn from him. So it is the time. I think we can start now, Rajiv.
Yeah, thank you. But as Bipin said, I basically come from a art science background or climate background, but um, with students and other, I also work on data-based analysis of climate science, and so some of the works which I am presenting here today and tomorrow are representing those works only, and. There's an interesting thing because at 1 minute may I have, so I'll just when I started doing PhD, I started doing data science or machine learning as a topic. What happened is that time it is, I think 2005 or six. Yeah, it's on. Okay. Yeah, so I think it's okay. So that time, what happened is physical models and machine learning models both were, you can say, in the same thing, but physical model won in terms of predicting the monsoon. So 2 chapters I devoted on machine learning. Then that time, few renowned scientists from meteorology told, "Oh, look, these are all data-driven, empirical, this and that, and these things, and it works not better than the physical model. So you will have you go to shift to dynamical model, so-called other model." So I shifted my second chapters and others are in the physical model. Although I understood that it was done, so if you are a art science researcher from an art science background, you will always face this dilemma that there is a physics-based, understanding-based model, and there is a model now, machine learning. Now, the machine learning model which we are now working came hardly 10, 15 years back, right now, whatever we call this deep learning era and other things. So it's still not the last word, but the physical understanding which we develop, and if we can club both together, I think that's the optimal choice as of now. So my talk, I will first, as a earth scientist, I'll give some introduction to the machine learning models which we are using or which we come across, and then I'll shift to the physical problem, and tomorrow I'll more devote on the prediction part. So acknowledgements, I would like to acknowledge ICTS, IITM director, and the organizers here, and the people with whom I have worked on primarily on the machine learning models during my tenure at IMD. Yeah. So just to warm up, as I said, that Galileo did a lot of experiments in, he put a wedge and then he kept a ball, and then those balls coming down from the inclined plane, and they measured the distance, and then so and so thousands of experiments were done, and people came up with some rules. So there were experiments and there are rules. And now when I have some data and I want to get some answers, I was following, I wrote a code and I get some answers. So that is the traditional physics-based rules. Now, why I put God here? Because not only physical aspects, here you can have like language, for example, or anything which is very powerful in the sociological context, which does not at all follow a physical perspective initially, that becomes the thing. Now, what is this in the current era? Yesterday, that 4th PI person told CHR that this is the machine learning, and the rules we are deriving, because now we have a lot of data and we also have some answers to the data because we are now experimenting. So we reverse calculating the rules. Okay, the beauty of this approach and this approach is that here the rules are here based on scientists and some given societal or some spiritual or philosophical. Here the rules are coming from the data. So is this equal to this? Well, that is a philosophical question, but the point here is that anybody can make this rule. So even if you do not understand the physical concept, even if you do not understand the context, just by looking at the data and the answers, you can make it. Of course, the data is now become the gold mine, and other rules like physical rules and other things which this machine is making. So you need investment in the machine and you need this. So this is the basic paradigm which is a shift from the models here and which is shift from models here. Now, the data-driven tools in climate science is not new. For example, the climate data always starts, or whatever way we taught that some tendencies we are calculating, like wind tendencies or temperature tendencies, which we are calculating, and those have some fixed equations, PD, and we have, this is the mathematical representations of the model, and we have some technology. So in the past generations models, those who have worked in the 50, 60 years of machine learning models, they have come up with finite difference model, like UK Metaphysics, whichever we have done. Then we have spectral models. Then we have in the finite difference, we solve for staggered grid. Then now it has come finite element volume and finite volume V3. Okay, so there are a lot of grids. Now, a few years back, ECMWF make a library of different types of grids and optimizations and how you can solve those. So the goal was to solve these equations, the tendencies much better. So in a sense, that is also a data driven, but we are trying to get optimized solutions from these equations. So machine learning is always good to introduce from a general perspective. So what is the general perspective? We have big data, and we have say huge observations, or we have say a big dictionary of different languages. Okay, so and then we have to come up with a decision. The most important thing is that what we heard in IMD. Okay, so tell me what is, okay, I say this is a model, we are using best advanced model in this world. And then when you go to the user or stakeholder, they always ask one question, okay, so say, okay, can I plant this crop, or do I need to add fertilizers this week or the next week? So in other words, from the user perspective, those equations or having those equations or not having those equations have a different context. So they are always asking for the impacts of my forecast. So that is now called as the impact-based forecasting. Okay, so it's not necessary that you get a forecast and a user would understand the forecast. The necessity is that the forecast application is very much target oriented. So this is what a purpose, and in that context it is found that in terms of taking decisions, okay, there are two ways: either you employ a huge number of person, or you make who will look at the individual sector, individual requirement, or you employ few people, but they are having some machine learning based tools or some automated tools who can take the decisions for this. So this is what is so in a way machine learning was introduced in the last 15 years in this way. So I still remember people who are working in the traditional. So, and you know, there are comments still made, okay, you need machine learning because they improve the forecast, okay, or you need machine learning because they take better decisions based on the output of the forecast. But science, okay, that's not the science, okay, so keep these things separate. So slowly, machine learning got introduced in the community as a better decision-making process. Purpose is to make decisions rather than this. But then soon there are few revolutions happened in the last 5-10 years where these people started believing, okay, let's say it's not just about getting a data and a decision model. There is some scientific part, but it's lies in you persons who are working in this field is to have a better context of using a machine learning forecast. So we have a physical problem and we have tools. Okay, now the tools, what does this tool do? One of the tool is the machine learning. Otherwise you have a old school statistical methods which you are doing. For example, you have a so what basically we are doing in using a machine learning is this. There may be additional tasks, but these are some of the major tasks. Okay, so which are actually required to perform, and these things are essentially machine learning models are helping in our community. And the process is now pretty standard. You have an input, you need those input in a particular way, that is a data gathering algorithm, and then you have to segment those data in a way that your extractions can be done. So we can tell it as a pre-processing, and then the feature extraction classification that is done, and then the post-process, and finally the output. So this is a pretty standard method now in all machine learning algorithms. So whenever, because it is a data-driven model, we often get confused that, okay, how to do a machine learning based pattern recognition. And so these things which we do intuitively, but it is better to have a modular aspects in it, because once you have a modular aspects for the sensing, segmentation, and then the machine learning models comes and they post processing, it becomes very easy for everybody that we get the results. Like we can change one module and add another module, so it becomes easy for programming sense. So one important thing is dimensionality reduction. Okay, so dimensionality reductions have two aspects. One is the feature selections, another is the feature projections. Okay, so these are some of the feature selections algorithm, and these are the feature projections algorithm. Of course, I have not worked with all of them, but here is an example. For example, this is a vector time series evolution of something, suppose a lino in a vector space. Okay, And we have three principal components here, and it is evolving. So these are some of the cases. Of course, this is done for some other studies, but I am just keeping it here. Now, if we project this thing in a two-dimensional plane here, it looks like this. Okay, so the concept is that we have a series here and we have to get the features of interest which we want. How to do that? Okay, now these are some of the methods which we are normally doing. So probably you all have gone through it, so I'll go through quickly, but still I'll just made this thing. So the wrapper method says that, okay, we have something, there is no, initially we have no features, and then we have some feature searching algorithm and then evaluate the performance. And if we get the best performance, we say this is the final model and we put in the test data. If it is not, then again we search. So like this, it is a iterate. So here, machine learning algorithms are always a iterative way of doing it. We do not do everything at a time. We build up based on some error mechanism. We slowly build up the model. So that's another difference with the traditional model. So there is now filter. We all know we filtered the data because there is a, so in monsoon, for example, you have low pressure systems, you have something called MJO, or you can have something called a mid-latitude waves. All those signals are coming together. You need a filter to understand each of these components. So those time you will use the filter method. Now, this tree-based model, so before the advent of these modern generations of transformers and others, tree-based model become very popular in some years. Okay, so there are a lot of, so these are called decision trees, random forest, and probably every one of you has used some of them. So for example, I plot here is a sense of weather, and then my ultimate target is to see the play. Okay, so we create some like this set of arguments where we will yes or no, and then based on the question we are asking is whether a person should go out and play. So based on those arguments and based on your index, which we are using here, and this can be numbers also. If it is a rainfall based, suppose we get a cluster of, so here our decision is like, is the rainfall is suitable for agriculture water or not? So then we will put last five for humidity, we will put temperature, we will put soil moistures, and we will put many other, and then finally come up with a regression based on these outputs. So next concept comes is the learning. Okay, so the learning part in a machine learning is doing three purpose: is a decision process, then an error function, and the optimization. So for a particular decision process, I employ a learning, and then we get the error, and then I am correcting that error. So this is what in the way every model is learning. Now, there are two types of learning, okay, the supervised learning and the unsupervised learning. Okay, supervised learning is like we have, so we have a labeled data and we have a unlabeled data. So those labeled data, if we have labeled data, then we can create a supervised learning algorithm. The unsupervised learning, well, which I worked sometime mostly, is like using unlabeled data. So from like nowadays, like when the data algorithm discovers pattern and help clustering or association problem. Okay, this is particularly useful when, for example, we do not have a labeling of the data. Okay, now suppose I give you that the rainfall is less than 2 mm, it's a dry day. If it is between 30 mm, then it's a moderate rainfall. If it is above 60 mm, you have a heavy rainfall. If it is 112, it is very heavy. Then 212 is extremely heavy. So I get those levels from IMD. You get anyone search this thing from IMD. Now those are the levels which are fixed. But how those are fixed? Okay. People have used different algorithms, but these are concepts of a level data in terms of rainfall classification. But if you do not have those levels, what you will do? So that is those times you are going to use a unsupervised learning algorithm, and you can actually get very good answers, and probably you can regenerate those things, provided climate change has not changed those levels. Okay, so earlier there may be those levels, and then recent. So you can very easily try based on some unsupervised learning. Say in 1950s, what it could be the extreme event in 1970s, what it could be, and nowadays what it could be. So you can have this thing, or you can then try with the full data and then use try with the difference. By the way, IMD has a very long history of rainfall data. So all machine learning algorithms, if you want to work, it could be very useful, and it is available in open source partly, and also for Indian universities and researchers or research institute, it is available mostly freely. The purpose of the training is to get this error function minimization. So what it is doing is actually we are slowly learning from a state where we are trying to get the minimum. So the idea is to add the error which is sign opposite to the derivative. So if it is x is increasing in a direction, my error function should decrease that direction. So that's how we are slowly training it. Okay, now here comes the concept of batch also. Like if I want to use whole data as a training, or if I put a few small batches and then we iteratively do it, then also it becomes a very useful. Normally we do it in batches. So the broad framework is like we have supervised, unsupervised, semi-supervised, and these things I will not go because I have the examples are given here for these things. These are the two right now thing, but it is just I have kept some examples, non-climate examples where these algorithms became more popular, and climate algorithm, of course, we are going to see it here. Now then deep learning algorithms came, where we are trying to say, so we have this deep learning inside this broader circle, so we are going to go there. But before going to deep learning, what is the right now so we all know that this is a neuron. I mean, is this everyone in this hall has seen this structure? Who has not seen it? Anyone? This neuron, single neuron, and its use? The last week, okay. So but people, has the people used it? That is what in this training course is okay, it is supposed to be, but has the people used this structure, have given a thought on this structure, what it is actually doing? Anytime? So this is not an exam, just you frankly you can tell anything. So this is a similarity diagram done, but I'm not going to do anything here because I don't have a knowledge about it, but this is similar to what they are doing it here. So this is based on the model. So if you have a set of inputs here, okay, so the purpose of this is to create, first you create this linear transformation, okay. So this is very simple. Suppose you forget G right now, okay? If you forget G right now, this is W. So these are some set of numbers, and you multiply it with these vectors, and then you add this bias. I'll come on this word there. So you see there is a dot product between the weight and the x. So it's just a product of how you are getting. So this is a linear equations, right? This is a regression equation, which we all are very familiar in any data. But this is depending on the number of weights, it would be a multilinear regression. Okay, so that is the multilinear regression, and sometimes your model, if suppose B is not there, this is actually what it is projecting the X, okay, with some output Y. Okay, but the point is my projections are not correct, because in a linear regression you always have the error terms. So those error terms you are adding here. Okay, so then this is a linear part. So it's nothing, first order, it's nothing. We have a input and we have weights, and then those weights are actually projected onto the some weight, and then we get a linear transformation of it. So in a first order, first term is the linear transformation. Okay, what machine learning does is it acts a nonlinear function G, which is called the activation function, and then that activation function actually gives the output. Now, so here comes one thing. If your data is such that the linear transformation is sufficient in the problem, you do not go to a nonlinear machine learning problem. So this is the first part. If you are sure that my data plane is such that it, like I showed one diagram of the Enso evolution in 3PC space, which is very highly nonlinear, and this is the, so you should think of going a machine learning space. If the data is, if the climate data which you are using, of course, in climate data mostly it is not, it's a natural data time series, so you have a lot of other things. So naturally, it is expected that in the climate data, these type of things would work very well. But if it is not there, then linear transformation is sufficient. But otherwise, you add a nonlinear term. If you put a nonlinear term artificially in a linear system, then you are going to get a bad classification or bad result. So that is has to be avoided. So this is what the main thing is. So the thing, that's why the concept of big data comes, multiple index comes, multiple type of text come, resolutions comes, and many other things come. So this is what I wanted to tell, that it is basically first order doing a linear transformation, then we are adding a nonlinear component, and the nonlinear component is good only if you are going to have a nonlinearity in the data itself. Okay, otherwise it's not a good idea. So some of the machines which I have given here, so these are coming. So in the recent history, actually since 2000, actually 2012 or 13, when this CNN type of, which I will discuss, came, it becomes a completely different than these traditional algorithms. And then there is an explosion of theoretical as well as fundamental concept, because there is a transformer thing introduced in this literature, which actually does two things. First, it does a speed up. Second, it does some very interesting physical concept, which are actually very useful. So now it is a computer vision. Now so many tools are available, so many concepts are available, people are connecting. I'll go there. So, but this is the first layer of models which people are very much familiar for long time, maybe more than 50, 60 years. And or at least 86, when backpropagation, there is algorithm which is added, then it becomes the current form. But people were facing some bottleneck. That what was the bottleneck? Okay, that this model is called multi-layer perceptron. Okay, so this is one of the oldest type of models of versatile use. Still, its use is not is not discarded, it is used, but it is used in combination with other things, so that what other things are not good, that is what we are going to see. So the limitations, as I said, that they failed to extract features. Okay, there is something called a vanishing gradient problem, where when you are training, you're training because in machine learning, one component is that at the end, in the training stage, the output y cap that you get, that y cap is not sufficient. It is feedback in the input side, so that you optimize your network based on this. So if the error function is very much bad or non-existent, vanishing or exploding, both way can occur, then it is not useful. So in most of the modern problems, in the modern problem, I mean when people started using text translation, for example, or started exploring figures, complex figures, for example, images, for example, and complex videos, for example, or in our art science perspective, complex models, for example, when we have so many data and we are trying to integrate, so it becomes clear that these type of models are not sufficient. So these are the two operations which actually since 2012 when it started. Okay, so two important concept is convolution and the next line text prediction. So convolution means you have some image here, and that image, okay, you can put some, you improve the resolution of the image. You can make a better representation of the image by adding colors, depth, and many other things. So this is based on the convolution operation I will show. So this is the purpose, one type of purpose. The other type of purpose is like what we are trying to do here is predict the next text here. Okay, so for example, deep learning is you put it in a large language model, which will give you some approximations. Okay, so one of the best suitable point is 43% probability is the powerful. So it does a sequence-wise, one step at a time prediction. So given the past step, we are trying to predict the future steps. So this is the purpose of this large language models. So this convolution and attention after the multilayer, these are the two most important concepts that has actually changed the perspective of how we model anything or how we estimate anything, especially in the time series context also it's coming. So normally there is a encoder for the transformer part. Normally there is a encoder part and there is a decoder part. And so when we are translating it, for example, from one language to another language, so this is how this thing. So we have a input text which is pre-processing, as you remember. Then we have the encoder, and then we have the embeddings, and finally the decoder module gives the most probable answer to it. Similarly, the convolution is actually giving your word here and then so as I said, whether this and this, at the end layer, there is always a MLP layer, multi-layer perceptron layer. So the usefulness of multi-layer perceptron is not actually, you can think it of a gigantic pre-processing that we are doing before feeding it to a feed-forward network or a multi-layer perceptron. And those are the pre-processing which has actually revolutionized this type of problems. Okay. So, for example, so anyone taught this convolution, Adway? Okay, okay. So there are convolutions like 1D, 2D, and 3D. So you have a sequence and you have a matrix here, and you are trying to do this multiplication, matrix multiplication, and then you get a destination layer where it is shown here, so that you get the optimization here, how we are doing it. So it is one-dimensional, two-dimensional, and then this is a two-dimensional with adding multiple channels to it. So there are, so this is in a brief, and then you do some additional operations which we get the output of that convolution. So it's just like in which we are doing when we are using monsoon time series. If you see any the time series, we get lot of noise. So what we do is like filtering. We do Lankos filtering or many other filtering. Actually, so what we are trying to do, we are removing the noise and we are getting the most dominant variance state in the model. So how do we did it in linear models, linear sense? First, we do a power spectrum, for example, and we find that the power spectrum shows the most highest peak at a particular frequency. We took the coefficient, Fourier coefficients along those power spectrum line and then reconstruct the data with those power spectrum. So it's the same thing, but it is done in the context of image networking, that the most dominant features in the data is represented here. So this is what the stage is now. So there is a convolution operation. Then you are pulling it to a better feature, better learned features. Then again, we are doing convolution pulling. Many times we are doing it. And then finally, we are flattening the results. And finally, we are putting to a fully connected multi-layer feed-forward network. And we get the final output. So this is what the convolution has done. It has used the raw input and it has done step-by-step feature selections. We are not at all doing all the feature selections in. This is a new concept in the filter, in contrast to the statistical filtering which we are using. That you do not filter together. You filter few features first based on a type of kernels, then you add new kernel and you feature from that. So if you do these step-by-step feature selections and the outputs are much better, and if you then feed it to a feed-forward network, your output is going. So the convolution network is not just convolution operation, is this operation when you are multiplying with the kernel, but the network when it is doing, we are doing it like so. Step by step we are getting the features in the data. So in the numerical model, forecast model, there is an example for that. For example, we filter out the sound waves in the Navier-Stokes equation when we do the climate models. Okay, because why we do it? Because it has no use. Now, for example, if we have to find a statistical, if we have to remove the nonlinear terms like advection terms, U, del U, del X, and those terms. I hope you have read those equations. So those advection terms, if you use, you get a linear term. So if you try, or sometimes we create a model where only one-dimensional advection is added, not the full advection layer is added. So like that, we do in a physical model, we do use those concepts, okay? Because if you add sound wave and your solution in a climate solution, geophysical flow, it will have no use ultimately, because the scale in which we are solving the model is at least for mid latitude, it is in an approximate, mostly geostrophic balance. Now, have you heard of geostrophic balance? Anyone? So it's a pressure gradient and Coriolis force. That's the most beautiful constraint of any equation we have. Now in image, we do not have those constraints. So people slowly discovered it, but those constraints actually exist in a geophysical flow. Because if you see a mid-latitude flow, you will see the pressure contour and the winds are flowing parallel to the contour. So what constraint that? Why not anything? We know nature is a so much complex thing, but why a flow does not have any direction? Of course, it has any direction it can have, but mostly it does not have because of the synoptic scale motions for which the weather we look is in a geostrophic balance, and that's a beautiful and that's the most interesting constant which already nature gives, and it simplifies a lot of things. In mid-latitude, the weather systems are dominated by those type of equations which filter out all other things, starting with the geostrophic balance. Okay, so such constraints are there. Here, you do not know what is the constraint. As I said in the start, machine learning model learns those rules. Okay, nobody has to tell that it is irreducible. But if you add a mid-latitude model and you get it, you will get the geostrophic balance in your equation. So next comes this transformer models, which I will tell. Okay, there is. So before that, let's go. Okay, I'll come back to this slides later little. So first is, before going to the transformer model, what we are doing is we are having the RNNs, okay, recurrent neural networks, in which what we are trying to do here is, for example, we are putting sequentially inputs here. Okay, suppose this is has to be translated. Okay, and we put one at a time, and then we get some context here, and then so this is the encoder decoder type, and we get the translations of this thing. So there are two things here. One part is, if it is a very big sentence, so and then we get it here, so it is highly very possible that in a big sentence, when we try to do, we forget the data that is to pass. So the long range relationship is forgotten. Okay, and we need to wait. So because this is a step by step trying to do, we need to wait that serial calculation, all the steps are calculated, and then actually we are trying to get the processing done. Okay, so these problems are actually very much problematic. So but one thing is, solution is long range memory. What we can do is we can add everything to some additional layer we can keep, and then we get. So yesterday someone has shown UNet, and it is connecting the UNet input to the last line. So it is some way telling that don't forget the initial state. You go around this all the loop of U, but you at the end of the state you have a U. But here again, the point is, still you have to process the data like this. Okay, so these things has to be removed. So what this paper, 2017 paper, attention is all you need, is they revolutionized this concept, and they have actually created the concepts of a model which these things are parallelized, as well as they solve those attention problems. So this is the actually attention module here. So it contains the encoder decoder part. In the first part, you have the encoder, okay, where you are actually having something called a attention multi-head attention layer. Okay, so I'll come to that attention layer later. So then you are putting these things to a feed forward layer, and then this is NX, it is mentioned. So in the original paper, it was 6 actually. So you do this loop multiple times, and then you get the full structure. Now, what is this attention? So remember, the purpose of attention is that it does not forget the past part of the language. Basically, it has arrived from the language. So these inputs, they actually same input, we give some weight vectors to it. Okay, now so it's like a what it is doing is, it is taking so they are calling it the query, key, and the values vector. Okay, so the queries and the key, the transpose of the key, if they do a dot product here, okay, now then this is what they propose. But there can be these queries. In a sense, query is the word which you are trying to see. For example, the bank of the river is flooded. Now when I am asking for the bank, it is not a bank in the sense financial bank, it is a bigger river bank. And then it is this bank is flooded. So this is the most important word. So the keys and the queries are arranged in such a way with respect to these weights. Now these weights are actually learned when we have both the data, it is learned. So when we add those things and then we do a softmax normalization, now there are reasons, as I said, always these things work better for machine learning models. And then finally, if you multiply it with the value vector v, you are actually getting this attention as a function of QKV. So the point I am trying to tell here is that the problem of long range memory solved because you have a key vector which is transpose of the key vector, and you have the query vector if you multiply it. And so I'll come to that again, what it is doing. So this part is actually, in a way, you are actually, once the input part is embedded as a vector, this problem is long memory problem is partially solved. Okay, now mostly solved, because then you have to do multiple times of the same things in the same layer parallelly you can do, which is called multi-head attention, or the other you can do other. So I'm coming to that multi-head. So if you have similar head together and you concat all those head, you can, so multi-head is working, of course, better than the simple one head attention. That's how they claimed actually, and it is true perhaps, but I have not checked. Okay, so the point I'm trying to tell here is, building the large language model, we have two stage here. One is the data preprocessing, then attention, you have to shift the attention mechanism, like you do a dot product attention or a additive attention, whatever they have, then the large language architecture. And then we have a foundation model where we are initially first order training, and then we have a fine-tuned model where we are training it. Then the final classifier results come. Okay, so this is how, why I am telling this thing in details, because one of the most popular model or many models are now using attention in their forecast. So for example, Pangu weather, it uses some form of attention, and it gives a, when I am discussing the next class, I will discuss that part here. Okay, so I think this is the model part. So let's go again, the attention. So why it is a transformer. Okay, so it is transforming information. Okay, so long range components there. So just like Fourier transformation we do, and we have a Fourier neural networks where we first Fourier transform it, and we actually, then we do the all MLP processing and other things, which is done. So there is a popular model, NVIDIA ForecastNet, it uses a Fourier. So it's again using a transformer model. Okay, so what I'm trying to say is, this is not unknown to climate science in the data perspective, because you have this query times k transpose. This is the dot product or matrix. What you are getting is, along this diagonal, you are getting the covariance. Okay, sorry, variance rows. And in other places, you are getting the covariance rows. Now, these covariance actually connects the one row to the one value of x. Normally, what happens is, if you do a eigen analysis of it, okay, you add you just take a determinants and minus lambda, what you get is the EOF. Okay, so in that case, you just remove those covariance, means we are just transforming it along this axis, and we are getting the EOF. But what these metrics give you are the long range relationship between this row and this column, okay, like this. So in a word processing where we need those long range relationship, we need these all the components to be preserved. Okay, but in meteorology, when we are trying to get a linear model, for example, you take sea surface temperature, you put it in the, take the anomaly, create the covariance matrix, and do the eigen analysis, you will get the El Nino. So some of the things in linear mode you will get, but sometimes some things you will miss. So I'll come there in that model. Okay. So next comes the vision transformer, where we are actually image. So the same concept has been is trying to separate between different classes. Okay, again, it's a class-based algorithm, and in a vision transformers, okay, we are using the same concept, but here now instead of language, we have input as image, which we are linearizing it, and then we, because image has a positional significance, we add a positional vector here, and then we do the same type of processing, add attention layer to it, feed forward it, and then we are doing that. So it is this layer is given here in this model. So what I'm trying to tell is, earlier there was CNN, we are using CNN condensal filters. Now, because the transformer says I can have the long range memories in a much more suitable way, we can actually, then people tried it on the image, and instead of getting the normal CNN based convolution, now it's the attention based model which people are processing it. So there are, in the computer science literature, it's always two big giants. Okay, still what happens is, for lower number of image, for example, the ResNet is still good. Okay, vision for higher training, so it is more than 400 million image. If you train it, actually you have a just 3-4%. So now they are training 3-4% is a very good percentage. But I am telling just, but it is not a, but as you see that there is a thing here is that for climate data scientist, pattern or a image, okay, and the text pattern or a image, well, they are well related, okay. Can you tell me that, so what I am trying to tell is, transformers originated from sequence to sequence modeling, like a time series modeling. In convolution layer originated from image classification. For example, El Nino or La Nina, I want to label those things. Okay. The point is, for a climate data, both these things are related. Okay. How you can tell that? Anyone? Because the physical process which we have got in the climate data are, if we think of a wave type of perturbation generating, we have a dispersion relation, okay? Now, what happens in a dispersion relation, a El Nino cannot change its phase in a month, okay, or in a day. A Pacific pattern, large scale pattern, you can have actually, it will take its 5 to 10 years time. So when we are talking of El Nino, naturally we are talking about a long time scale pattern. So because of the dispersion relationship in the climate series, things are actually, it's already somewhat decided what type of wave and what type of things we are going to do. But anyway, they are the computer scientists are proposing that those things are actually, you can combine CNN transformers so that there is no, both are happy. Okay, both community is happy. Okay. Now in climate, last 10 minutes, I'll just give the climate example. But we have some question answer. Okay, tomorrow also we have, tomorrow we'll have, but because this is, I am just trying to make the more model here, because without this, the question answer would be immaterial. Okay, I am here full day, so anybody can ask questions, so no problem. But let's finish it because why I discussed those things in elaborate, these are applied here. So this is the rainfall time series, for example, and you get a filtering. So, okay, so this is, so you have a very high frequency fluctuations and you can have a very low frequency fluctuations here. Now, as I said, the dispersion relation curves are this. Okay, you get from theoretical models, these lines are the Kelvin waves, these are the equatorial gravity waves, then these are the Rossby waves and this thing. The point, what happens is, if you plot it here, you get something which is not predicted by these linear models. Okay, we get some patterns here. These things, climate, it is called MJO. This is a signal of MJO. So, but before going to that, you see that Kelvin wave as it is. So some wave numbers can have a particular frequency. So if you are trying to understand the properties of a Kelvin wave, you have inherently have a spatial and a temporal scale. Those are related. Okay, so it's not okay everywhere the Kelvin wave power is not dominating here. Okay. Similarly, if you see the monsoon time series, we have a few band of sharp frequencies which are actually there. But the point is, in monsoon also you get some, if you do this thing, you will get a band here, which is not explainable by the thing. So then comes the perspective of using the machine learning model for climate. Now, this is what I was trying to say, that we get a model, we solve this model using these equations, and then we get these relations. And this is one pattern which you have seen. There is a nice systematic propagation of rainfall from equatorial band to this thing. But this pattern is not available from the linear dispersive models. So then how to study them? So that's why the machine learning models, we have started using it. And the most important thing is, what should I use? Because there is no labeling concept here, I should use unsupervised learning. Okay. So as you see, there are waves like this. Okay, so what is the structure? It moves eastward, it moves northward during monsoon. It has a power spectrum like this, and it is embedded in a multi-scale cloud structure. Okay, now in such a system, complex system, so we are naturally inclined to a big data type of scenario. We do not have to additionally strive to find index. We have a big data type of scenario. So understanding this thing was holy grail perhaps 25 years back, but now actually even the understanding is there, but even prediction is still not completed. Okay, so similarly there are mid-latitude waves, for example, quasi-geostrophic waves which are there. Similarly, there are equatorial waves are all there. Okay, so these are the two concepts. So because I think tomorrow I'll start here, and then we'll finish from here. So what we are trying to do is, we need to catch the observed pattern in a better way, and we need to analyze and simulation of the intraseasonal oscillations. So intraseasonal oscillations, which are so dominant here, some part of the spectrums even don't come into the linear structure. We are trying to understand those. Linear methods are available, okay, but what the nonlinear methods will teach us. Okay, so we will do dimensionality reduction, but that part again I'll start tomorrow in my lecture. Okay. Yeah.
Thank you very much, Dr. Chattopadhyay. So now he has given the time for some questions, and I think he has told very basic things, and definitely we will have the questions. So yes.
The 1 hour track course on the machine learning last week, they had a detailed illustration of all the concepts. These things taken together, but not familiar with much familiar. There are two questions.
Sir, you mentioned about the attention mechanism, which focuses on the important parts.
Yes.
Similarly, something like principal component analysis also focuses on the important parts. So is it fair to like draw an analogy between them, or could we use attention as an alternative to principal component analysis?
See, attention is, if you see the variance covariance thing, when we do the principal component analysis, we linearize it. So that lambda, if we do the matrix and get the eigenvalue vectors, those eigenvectors are the linearized functions. Then in meteorology, what we do is stratify them in terms of eigenvalues, the variance explained by these things. So highest variance explained, we say those are the most important. In attention, what they are doing is they're considering those diagonal matrices. So they are not linearizing it, but they are also considering the long range part of it. In meteorology, it is still remain to be seen that what is uses, how to get that thing. Number one. Number two, the success of the prediction mechanisms like Pangu weather, which uses a transformer called swing transformer, which is a shifted window transformer. They are doing it. It illustrates that this mechanism has a future, because it's not only taking only those linear operator components along the diagonals, the off diagonal elements, other elements, which are the long range importance thing. That is, the point here is, in a language, the sentence is not very big, okay? Or 10 word, 20 years, Shashi Tharoor can make very good sentence with lot of words, but normally in climate, we do not know how much all attention giving the full structure is required or not. So it's not still generated. So it's up to the researchers to tell which are those long range memory components, those are to be focused, and which long range. But that classification, to my knowledge, has not yet come in the climate part. Okay, so yes, it is important for all the components if you have to do prediction. For understanding, like, linearization is a good way to start.
Thank you, sir. Thank you for the wonderful talk. Sir, actually, we learned that multi-head attention performs better as it focuses on various multiple perspectives of the data simultaneously. So I was curious that can a transformer be trained jointly on multiple variables like SST, pressure, simultaneously, so that we can have a multivariate projection, something like that.
You can train, but the point again is that it has to be physically related. Okay, if you train, for example, stratospheric ozone with, for example, SST in the same dimension you have, probably you will not get much information out of it. So physically related variables, if we add multiple channels in it, so the success of models like GraphCast, for example, if you have seen, I will talk tomorrow something. So they have huge dimensions in it. So they don't care what, and then they put those graphs on it, and then they train it. So they filter out some thing, and they keep something based on it. So yes, you should train it with multi-head attention. In terms of attention mechanism, multi-head is a better option than the simple this thing. But also remember that don't keep everything to the model to understand it. Then you will take long time to do those variable selections in your work. Okay, so use some physical arguments, then you train it. Then I think it would be better.
Multiple data. I mean, it's not multiple channels. So multiple data, you have to choose whether they are correlated to your target variable or not. It doesn't matter if you are using the convolution or you're using a transformer. Both the places you can use. Transformer has the special feature, that is the attention. So when you are using the multi variables, it will use this attention mechanism will apply in all the variables. So it is like fundamentally this is different. So there is not a relation that if it is attention can be used the multivariable. You can always use.
So for example, ENSO monsoon relationship. ENSO in February impacts monsoon in June. So it's a long range relationship in the past sequence. So in such situations, you should use SST in the past and forecast the rainfall. So because they are long range related. So they are the transformer type of situation. But if we have a monsoon low pressure in the Bay of Bengal and we are trying to get the rainfall, so there the local image is more important. There the convolution part is also. So that's why both the things are important in the context of use. Okay.
Other question? There is anything online? No? Adway? No. So there is no online question. So we thank again Dr. Chattopadhyay. It was a very energetic talk. I mean, okay, so we will go to the next talk now, and I hand over to Adway.
Okay, thanks a lot, Dr. Rajib Chattopadhyay, for that talk.